CSP seminar today. And for today, we're very happy to invite Professor Xiaochen Wang from Purdue University. And Professor Wang is currently an assistant professor in the ECE department at Purdue University. And she received her PhD degree from the University of Pittsburgh in 2019, and also the bachelor degree from the Georgetown University in 2013. Her research has been very interesting from like the meetings today. I believe most of you maybe have already seen that, and also during the different conversations. And her research focuses on designing the novel machine learning methods for the interpretability, fairness, and also the robustness. And she has also got the very interesting applications in the healthcare and also biomedical informatics. She has received many awards, including the NSF Korea and also the AAAI Distinguished Paper Award. So let's welcome again for Professor Wang to give us the seminar for today. Thank you so much.
Do I need to wear the microphone or I should be fine? Yeah, I can try to speak loud.
Yes, I think maybe for the room attendance, we can
Oh.
use the micro that can work better. Can put it on your. I already turned it on.
Thank you.
Okay, yeah, you want to put it here or on your pocket? Yeah, sure.
Okay, let's get started. First of all, thank you, Liu, for the nice introduction. Welcome today, and also great to be here today. Thank you for the opportunity for me to introduce our work in terms of fairness in deep learning. And then for our discussion, we will be focusing on two perspectives: data and model perspectives. So nowadays, we see artificial intelligence almost everywhere. The big like advancement and also fast progress and wide application of AI has been spread out in different areas, like in terms of face recognition, medical image, chatbots, like clean chats, like predicting protein structures and so forth, drug discovery. And then we have seen amazing performance of AI models, but also at the same time, we saw some prevalent concerns of the models. And then for today, our discussion will be focused on algorithmic fairness. So here, let me give you some real world examples in unfairness. So for example, in healthcare, people found that the model may have different performance in people from different race groups. And also in criminal justice, advertisement, recruiting, search engines, so on and so forth. People found that the model, even though seems to be powerful, but they bring some different performance when faced with people from different demographic groups. And this is definitely a very important, severe concern we want to address. And also recent days, we have large foundation models. They are able to handle lots of different tasks with amazing zero-shot capabilities, but also at the same time, bias has been found in large foundation models. So for example, when we use GPT, the chatbot, then people found that there's severe relation violence bias when we ask the model to say finish a certain task, complete a certain sentence. And also in text to image generation, if we want the model to say generate images of a certain occupation, then the model also shows some gender bias in the generating models if we use the stable diffusion or DALL-E models. And also if we want to use large foundation models in zero-shot object detection, and then in this case, suppose we want the model to detect either nurse or doctor in the image, the model shows some bias like towards certain gender occupation pairs. So in the illustration figure, the top one shows the bias term because they didn't detect doctor or nurse from a certain like gender group. Down below is more like a desired version, like after the bias scheme. So down below is the performance we want to get, where we maintain the good detection, object detection performance, while also avoiding like severe, like lower performance in a certain demographic group. So that's our focus. And then before getting into the method of addressing all the severe concerns, we want to first clarify how fairness is defined. So how to mathematically define fairness. So it's like, what is the goal, mathematically speaking, before we can dive into the method to address this fairness issue. So for fairness definition, roughly speaking, we can divide the concept into two parts. The first one is we are talking about individual fairness, where it just requires that similar objects will be treated similarly by the model. And then it has the like formulation, like a Lipschitz continuous term like this. So we may have a distance metric or metric measuring similarity between two objects, a pair of objects, and the output from the model, like the model behavior for those two objects, should be similar if the two objects, they are not too different. Okay. But for individual fairness definition, there's some flaws. First of all, the definition of similarity is subjective. So how do we define the distance metric or the metric to measure similarity between any pair of subjects is subjective. So we don't have a common sense to define that. And also at the same time, because we require the comparison of similarity between every pair of objects, so it is a little bit difficult to scale things up when we are looking at a large scale data. When we have a lot of, say, samples, then if we need to consider every pair of samples, then that will be like huge computationally speaking. And the third thing is there may be some legal issues if we need access to every single data, because in many cases, due to legal or regulations, we may not have access to every single data. All we have is maybe some group information, or all we have maybe is just an API model. We can have like a black box model where we can only get API calls to access the output. So in contrast to individual fairness, we have a other way of defining fairness, which is group fairness. And this is also known as statistical fairness. Okay. So for statistical fairness, the rough idea is it requires that the model have consistent performance in different demographic groups. And then the way to define demographic or sensitive group is we use, for example, letter A to show the groups. The group can be in terms of race, gender, age, background, geographic location, so on and so forth. And for group fairness, we require the model to have consistent performance, meaning that the model performance should not be too different for different groups. And then in terms of this, we may have different definitions for evaluation metrics. One is demographic parity, DP in short, which requires that the model output is independent of the sensitive group A. And also we have another definition of group fairness, which is equalized odds. It requires the independence condition on a certain target label to avoid in DP if we have just random assignment of the labels. And also we have another group fairness definition, which is minimax fairness. For minimax fairness, it means we have multiple demographic groups. They are noted as this letter A. And then our goal is trying to maximize the worst group performance. So meaning that we want to maximize the group that has the worst possible performance. So those are the ideas, and because for group fairness, it's more easy to scale up and also do not have the issues mentioned in the individual fairness. For our discussion today, we'll be focusing on group fairness. So group fairness will be our focus today. And then after clarifying the definition of fairness, we want to think about like where does unfairness come from? Because we need to know the source. Then we can develop method to address the unfairness issue or bias issue in general. So as for source of unfairness, data bias is actually one major source. Because if we train a model on biased data, then the model will just replicate or even exaggerate the bias from data, so make bias prediction. And then for data bias, it can be shown in different ways. As here, it can be from sampling, from stereotype, or from subjective judgment, so on and so forth. And all of this will result in we have a collection of imperfect data. So we have data containing bias, and when we use this bias data to train the model, then the model will show undesirable bias behavior. And then when we model this process, so let's see why training with biased data is a bad thing. So let's recall what happens if we train the model using ERM, empirical risk minimization. So the rough idea is like based on the task we have in mind, we are gonna have a loss function defined to show like the error function. And then the loss function is with respect to each sample. So suppose we collect a bunch of n samples. And then we are trying to learn a model theta such that the overall loss will be minimized over all the samples. So that's a normal way of training a model for different tasks. But if we look into the data we have in mind, so suppose we have a bunch of n samples as training samples, then some samples, they are actually coming from the majority groups. And then the majority groups, then we have a much larger set of samples coming from this major group. But for the other groups, we may have much fewer samples coming from the minority groups. And then in this case, what all we do is just divide the loss function into two parts. Everything remains the same. But if we do this minimization problem by finding the best primary theta to minimize this overall loss function, then the model will inevitably put more attention to this majority group because they dominate the training data. So the model will try to make the performance to be really good on the majority group because it occupies the majority of the data. But in contrast, for minority groups, they get less attention. So that is why the model tends to have lower performance for minority groups with fewer samples. So that's a pretty simple breakdown of data bias. And let me show you some example of the bias in practice. So first of all, I do healthcare stuff. I work on Alzheimer's disease analysis with some healthcare collaborators. So one thing we are interested in is to study Alzheimer's disease prediction using data collected from like a cohort. And then for this public cohort, ADNI is a pretty famous public cohort, famous for Alzheimer's disease study. But if we take a look at the race or ethnicity groups of the data, we will see that there's a huge imbalance in terms of the race or ethnicity groups of data. So we have majority of data coming from a certain populations, but for other race groups or ethnicity groups, they only occupy a very small portion of them. And then if we use this data to train a model and then we do equal weighting of all data, then the model inevitably put more emphasis on this maybe European population and non-Hispanic population, but the performance on other minority groups may not be as ideal. Okay. And also another example, so this is more like a society data, but shows the concept of object detection. So for this case, we want to do object detection to show what the bird type is. So we only, for simplicity purpose, we only have two types of birds. We have water birds and also we have land birds, just two types. And also when we capture the image, so it's natural that water birds, they are more likely to show up in water backgrounds. And also for images of land birds, they are more likely to be captured in the land background. But the background does not determine the bird type. It's just a spurious correlation. But if we take a look at the data, you will notice that you have much more samples that is water bird from the water background and also more samples with land bird with land background. But for the minorities, they are like the other two combinations. And similarly, the model tends to have good performance for this majority groups. So in other words, they try to use the background of the bird rather than any any features of the bird itself to do the object detection. Okay. So that's the second example of majority minority group bias. Okay. Another example of this bias data is when we do classification. And then, for example, for disease detection, in most disease detection, we have much more negative samples. We have more normal control samples, like benign samples, compared with the malignant or like the ones with disease. Especially for rare diseases, in this case, we have only a few portion, less than 1% of data with disease. Everything else is healthy. Okay. But in this case, if we train a model that is doing nothing, they just blindly treat everything as negative, the model get a performance accuracy over 99%, but this model does nothing. Okay. And also a fourth example in NLP test. So for here, we want to do sentiment analysis. And then for the training data, probably for the sentiment analysis training data, most sentences associated with Spielberg is something good. So they are just showing like how good the director is or the movie is. But in this case, the model will pick on the shortcut thing. So as they found the keyword of Spielberg, they will just blindly predict the sentence as positive, regardless of the content itself is actually negative. But similarly for maybe unfortunately in the training data, most of the content about New York subway is more like compliments rather than compliments. In this case, even though this sentence itself is a positive meaning, the model will pick on such shortcut of New York subway to predict that as negative, which is a false prediction. Okay. So how all of these are real world examples of data bias. Okay. And this is the problem we want to address in our first work. But before moving forward to the methodology part, I would like to clarify that for our talk today, even though we motivate the work with fairness, this is definitely very important and severe concern. But you will notice that for the methodology and the example we gave, many of the examples are not in the fairness domain per se. They are more like related with robustness or generalization ability of the model, if and also trying to address some distribution shift. So in other words, when we have biased data, it means the training data brings some undesirable information, and this undesirable information is shown as like imbalance across different groups. So in other words, methodology-wise, our model can be used to address fairness issues, but also it can be used to improve robustness, improve generalization ability of models. So in other words, we have a pretty broad definition of bias. And all of that is we have a concept of bias we want to address with respect to a demographic group or with respect to maybe the background or a certain concept or shortcutting a sentence. And then this is the information we want to kind of remove or address. So the first part of work, we want to address that from the data perspective, as promised. And then in this case, if we use this WaterBird data set as an example because it's relatively simple, then so in order to address this bias, data bias, so it's coming from imbalance of data, then the most straightforward way to address bias is to balance the data. And then to balance the data, we can define the bias ratio, and the bias ratio will be the portion of majority samples across all samples. And then in this case, if we have a majority like bias ratio close to 0.5, that means we are looking at more balanced data. But if we have a bias ratio like this zeta value close to 1, then very unfortunate, we are looking at highly skewed data. So this is the definition of bias ratio. And then for this debiasing method, there are actually already a lot of different methods proposed to adjust the bias ratios. It can be collecting more data. If possible, that's the best way, but that's the most difficult way. And then if we cannot collect more data, then we can do data generation, we can do data augmentation, we can do resampling, reweighting. All of those can help us to make more samples, to get more samples in the minority groups to balance this bias ratio, make the zeta value to be closer to 0.5. And in practice, this method, all of these methods, even though it's data augmentation or reweighting, resampling, they have been shown to be effective. But mathematically speaking, all of them, they are trying to adjust this bias ratio. And then for our work today, instead of proposing one more way to adjust the bias ratio, we want to find the impact of this bias ratio. So in other words, we want to know how balanced is enough. Do we really need pure balanced data, like fully balanced data? So let me first show you the results we have. So for the results, horizontal line is slightly different than what we show, but you will see that the x-axis is 1 minus zeta value. So remember, for this zeta value, closer to 1 means the highly skewed data. So in this case, 1 minus zeta closer to 0 means highly skewed data. And then closer to 0.5 means more balanced data. And then meaning that from left-hand side to right-hand side, the balance ratio is actually getting better and better. Okay. And then we have a theoretical study to model the curve. And then in all of these figures, you will find that we have two curves, one red, one green. And this red curve is the empirical observation. We actually conduct experiment on each of the bias ratio and collect the result. And the green curve is our theoretical estimation. So we have a theory I will show you later. And based on our theory, we are able to like estimate the model performance. So for here, the takeaway from this slide is just to show our estimation seems to be good. So the green curve seems to be close to the red curve. Okay. And we tested on different like models, different data sets. I will show you more results later, but this is a quick like slideshow of results. Okay. So this is what we want to do. And then in order to achieve the result, in order to do a estimation, theoretical estimation of the model performance, we first need to kind of have model the data distribution. So we start with the common distribution used in many existing works. So rough idea is we assume that the data, so for here, the data, they are the unobservation data. So we are talking about some latent embeddings of data like that is used for data generation. And we assume that this latent embeddings of data, they follow mixture of Gaussian. And then for the mixture of Gaussian, so for each, remember that we have different combinations. In the Waterberg data set, we have 4 combinations. And then we assume that each of the combination follows a Gaussian distribution. And then the overall data distribution will be a mixture of Gaussian, and their mixture ratio will be based on this coefficient, showing that the portion of data from that combination. And in other words, this p-value is equal to the bias ratio zeta we defined before. And then after we have, suppose we have the data distribution, then the next step is if we know data distribution, we'll be able to derive the Bayesian optimal classifier. Bayesian optimal classifier means the classifier that has the best, can maximize the accuracy on the data with distribution. And then we can have the formulation of the Bayesian optimal classifier like this. And also note that in the Bayesian optimal classifier, it has different terms. And in the terms, so this gamma value is related to the zeta value, like the bias ratio. And for the terms inside this exponential function, this m value, they are determined by the Gaussian parameters itself. So it's dependent on the Gaussian like mean and variance terms. Okay? And also the t value is just an indicator function. And C value is also something related with the data properties. Okay. So we are able to derive the optimal classifier. And then given data distribution, given a classifier, then we'll be able to derive the accuracy. We also derive the mass formulation of testing and training accuracy of the optimal classifier. And then based on the accuracy derivation, we will be able to model the change or be able to model the curve we want to have. So in other words, what we do is just model the change in accuracy. If we change the training data, zeta, like the bias ratio from a certain value to a different value. So from zeta train to zeta prime train. And then we will find that the change in the testing accuracy when we change the training ratio will be upper bounded by something like this. So for the terms on the right-hand side of this inequality, we will have that this m terms, they are something determined by the Gaussian parameters mu and sigma itself. So determined by the data itself. Pi is a constant 3.14 something. And then capital M is a constant, and this everything else is related to the zeta value. So meaning that the change in the accuracy will be determined by beyond constants will be determined by 2 things. One is zeta value, the bias ratio. The second is M value. M value is something determined by the data distribution itself, mu and sigma. Okay. And then in order to plot the curve, so because everything else is constant other than zeta and m, then if we can have a good estimation of m values, we'll be able to draw the curve at any zeta value. And then for this, in order to estimate the m values, then we just solve a math problem. So it's like we have 2 equations. We have 2 equations. Suppose we have 2 equations with different zeta values, and then m values, they are something we don't know, but we want to estimate. So if we have 2 different sets of zeta value, then we get 2 different accuracy values. So we have 2 equations, 2 variables, then we can solve that and get a good estimation of the m values. And then we put the estimated m values inside this function, and then what we can do is to draw the entire curve, no matter what the model is or the data is. So this is how we do the like theoretical estimation. And also we have like extended the theory to like more data sets. Because previously we showed some relatively simpler like smaller classifiers or smaller models like ResNet 18 or like VGG. And now we have some larger models. What we just want to show that the model also, the estimation also works on larger models with maybe more complex data set, and also different types of distribution shift. So for example, so for the way to interpret these four figures, the left-hand side figure shows the overall result. And then we have three curves, and then the right-hand side three curves, they are just the zoom-in version for each individual curve. And then we will see that in different cases, no matter it's class imbalance is more like the rare disease detection case. We have much more negative than positive. Spurious correlation is where we have, say, water bird type, but we don't want the model to focus on background. And underrepresentation will be the Alzheimer's disease example we gave, where we don't have enough samples from like certain race or ethnicity groups. So those are all different types of data bias, and all of that we can model, like no matter what model we use, Variant Transformer, ResNet 50, we can like do more like based on different like tasks and models. But all of that, we can see that we have a like relatively good estimation performance. So meaning that for error curve, in this case, this dashed line is error estimation. So error estimation shows a good curve about the model performance. It answers the question of how balanced is enough. In other words, it gives us an idea about the impact of making data to be more balanced versus the generalization ability. Yep, so that's pretty much about the impact from the data perspective. So data perspective seems to be effective, but we want to clarify that balancing data size, even though it seems to be good, but it cannot solve all the problems. First of all, in existing studies and a lot of models, the inevitable trend with imbalanced data. So nowadays we see tons of pre-trained models. So they are inevitable. We have no control about the training data. So they are inevitably trained with imbalanced data. So if we go back to retrain them, then that would be computationally expensive. So we cannot afford that. And also the second thing is, besides data bias, there's something from the model itself. So we have something called model bias. So model bias just means the bias or some property, unique property brought by a certain model architecture. So imagine that we have the same data set, but we like build two different models, one CNN, one Variant Transformer. Then the model may have different behaviors. And this is coming from the model, but not the data. And then, for example, in existing study, people found that CNN tends to have texture bias. And this is also something unique to the model. So this is a model bias we want to address. So how to address model bias? Let's use this image again, the simple but effective, hopefully, example again. So let's consider our water bird, land bird example, and then our goal is trying to distinguish the bird types. And previously, we discussed the ways to adjust the bias ratio, and that is actually a statistical perspective. But we can look at the same question, but from a different perspective, geometrically. So if we want to look at the problem geometrically, then there's actually another category of methods addressing the same problem, but from a different lens. Then in this case, instead of adjusting the best data ratio, so meaning that instead of trying to make the data to be more balanced, what we focus on is to adjust the learned representation of the features. So let's clarify two key concepts. So one is called invariant feature. Invariant feature just means the features that are related to the task. So for example, for this case, we want to distinguish water bird from land bird. The invariant features, they are the features related to the bird itself, maybe the shape of tail, like maybe color of the bird, feather, things like that. And for spurious features, it means features that are not related to the task. So in this case, background should be a spurious feature. And then, so from the geometric aspect, people found that the separability of these different types of features is also relevant to the model performance. So have a simple example. So if, say, we have the image like this, suppose all birds look alike, no matter it's water bird or like land bird. But suppose we change the background such that all water birds, they are in the pure white background, and all land birds, they are in the pure black background. Then in this case, this background will become a feature that has super high discriminative power because they have really low similarity between classes. Then in this case, the model will definitely pick on such feature because the model is lazy and tries to find the shortcuts. And then, so this is the feature separability idea, like conceptually speaking. It just means how good the feature is to distinguish data from different classes or different groups. And then geometric speaking, we just want to make sure the environment feature is more useful, and then the spirit feature is less useful. So the model will tend to use the more useful feature. Useful feature means easy features or better discriminative power. And then if we can have a magic way to make the environment feature to be more separable, but the spirit feature to be less separable. So that's also what existing works trying to do. So for example, they try to mute the background and change all the background to be the same, like maybe piece of noise. And then we lose the separability of spurious features, but keep the separability of environment features. Then the model will turn to pick on the features with better separability, like the better ones. So that's the geometric aspect. Note that that's a different aspect because here we are not adjusting any data ratio, which keep the data to be skewed, but we are trying to adjust how good each feature is, like in the learned reputation. I hope the idea makes sense to you, but the question we want to answer here is how to quantify this feature separability. Because feature separability, conceptually speaking, makes sense, black versus white or bird versus bird. But we want to have a mathematical way to define such feature separability so that we can quantify that, we can also regularize that. So how to define feature separability? This is also something coming from like the study we introduced before. So in the study introduced before, recall that in the derivation of the Bayesian optimal classifier, we show that the optimal classifier is dependent on two things. And then you will notice a term called M. M is dependent by the Gaussian parameters, mu and sigma. And this is the definition, our definition of feature separability. And so in Gaussian distribution, it actually shows the Mahalanobis distance of a certain feature. And then for this feature, we can have a quick insight of the definition of Mahalanobis distance. So for a certain feature, so mu shows like how, so for example, for data from two groups, we have positive mu and negative mu. The larger mu means the features, they are more separated apart. And then for this sigma value shows the variance, so it just means how spread out the data is. So if we have smaller sigma value, then it means the data is more condensed towards this average, like mean value. Then the model will have, the data will have more like better separability. So in other words, larger mu, lower variance will give us better feature separability. So that's the idea of Mahalanobis distance to show the separability. So higher M values give us better feature separability. Then given this definition mathematically, it's more like our way of definition of feature separability, but we want to show if that's useful in practice. And then for this feature separability definition, what we can do is for any model that is, so for example, for our theory, given the model that we derive, so we have the Bayesian optimal classifier, and then we can model the dependency on like spurious feature in the prediction. And then the dependency or reliance on spurious feature will be modeled in this format. This seems to be simple, but please note that this tau value is not constant. So tau value is dependent on M. So it's not as simple as shown. But rough idea, we have a like a fractional like format between the two separabilities shows a reliance on the spurious feature in the prediction. And in practice, we definitely want the reliance to be as low as possible. So we want this L omega star value to be as small as possible. And we have derived a theory like under certain condition, this value will be monotonic with respect to the increase with respect to either the invariant feature or spurious feature. So in other words, in plain language, it means if the spurious feature is not super good, suppose we don't have like black versus white, this type of spurious feature, then what we can do to make the model to rely more on the invariant feature is by either make the spurious feature to be less separable or less useful, or we can make the invariant feature to be more useful or enhance its feature separability. So that's the takeaway. And then given this takeaway, what we can do is we can model that, we can add a regularization into our modeling, and then we can make the spurious feature to be less useful. And then we use the difference between the mean values to show the separability. And then for invariant features, we make it to be as separable as possible. And then we add this regularization to the optimization, and then we minimize this regularization to minimize the reliance on the core feature or invariant feature in prediction. And then for this model, we actually show some results. And then for the results, we have three curves, red, green versus blue or purplish. And then for the red one is the ERM is the like vanilla version. And then for the green curve is group DRO is a method to address distributional robustness, fairness. And this is a very famous reweighting method, or it can be called the method with the state of the art in distributional robustness. But this method is trying to adjust the bias ratio. So in other words, this green curve is trying to address the problem from a statistical perspective. And for our method, the blue purple-ish curve is from the geometric perspective. We add our regularization and we do not adjust the data bias ratio. So our goal here to clarify, we're not trying to beat group DRO because they are two different perspectives, but we want to show like purely focusing on the geometric aspect without adjusting anything in data ratio can actually achieve good results, better or at least comparable to the statistical perspective. I got a question. Yeah, that's a good question. Yeah, so the question is, how should we know, like, how would we know which features are invariant or spurious? So first of all, the feature concept need to be defined, like, to be determined beforehand. So in other words, we need to know what the spurious feature is beforehand. And then in this case, we don't need to find in the latent space, like which dimension is corresponding to the features, but instead, suppose we know like the labels, the data labels, they are definitely related with the invariant features. Then we have a bunch of data, positive class, negative class. And then so this is how we define this mu plus and mu minus thing. And then for the spurious feature, if we know that the background is the spurious feature, then we have mu plus spurious means all the images with the wider background. And mu minus spurious means all images with the like. Yep, so that's a rough idea. And yeah, so again, for this result, it shows the geometric perspective is equally effective. And again, we are not trying to beat group DRO because these two methods, these two perspectives can be combined. You can do data balancing at the same time to recognize feature separability. You will get even a better curve, but that's not our purpose. So we just show the perspective is equally effective as the statistical perspective. So that's pretty much the discussion on the theoretical perspective. We have a discussion about like from the Gaussian mixture assumption of data, and then we model the contribution of different factors, data ratio from the data perspective, feature separability from the model perspective, their impact to the performance. And so for now, the discussion, they are based on the Gaussian assumption. But in practice, we may not have guarantees, see like the representations or the models will be like learned in the desired way. So the next question we want to answer is, we want to know in practice how good the representations and classifiers they are learned. So for a model, if we see, suppose we still use classification as an example. So for here, we use the perspective neural class, and the neural class is for classification, we divide the model like a classifier into two parts. The first part is a classifier. This is the penultimate layer, like the second to last layer, just the last linear layer for classification purpose. And everything before the penultimate layer will be the representation learning. So we just interpret the model as two parts. We first use a large nonlinear model to like as an encoder to encode the data to a latent representation like subspace. And then we have a linear classifier to separate data from different classes. And then for neural clubs, it's more like a phenomenon people found in the study. So it found that if the model is well trained means the model is trained to almost like zero training loss. And then the model may have some specific, like interesting behaviors for both classifier and representation. And the reason we use neural clubs as the perspective is because we want to know how good the representations and classifiers are learned in practice. We definitely cannot pick a randomly learned one. So if we have a really bad like training scheme, then there's definitely no guarantee. So we want to have a training scheme that with guarantee. And also at the same time, neural clubs, it found some interesting phenomenon with theoretical guarantee. So we want to follow that direction to look into this like bias learning like stuff. And then for neural clubs in practice, like in existing literature, is usually learned in group balance case. So where we have group balance data, and then we have some interesting phenomena for both classifier and representation. But in group imbalance data, we don't have like thorough study yet. So in our recent work, we like discuss the neural clubs phenomenon. So it's like if we train a model, like well-trained model to almost zero training loss, then what will be the behavior of the model? The behavior of the model will be divided into two parts, classifier versus representation. And recall that separability is something important in our previous discussion. And we also want to model separability in here to model how good the classifier and representations are. And for here, we use cosine similarity to model the quality of the learned classifier and representation. So for classification, so suppose we see if we project the data into like a 3D space, like a low dimensional space for better visualization purpose. Then for the classifier, we have like the two very short lines shown here. So we measure, so for each class, we may have a corresponding linear classifier, and then we measure the cosine similarity between of this angle between the two classifiers. Because they are classifiers for different classes, the lower similarity would be desirable because the best will be opposite like directions for maybe boundary classification. And similarly, we measure the quality of the representation learned in different groups. So subgroups means remember 4 combinations in the water bird example. And then we will see that for samples from different groups that are in different classes. So in this case, the red one and the yellow one, they are from different classes. They are from the majority group in different classes. So red one will be the majority samples in the negative class, and yellow one will be the majority samples in the positive class. And we also measure the cosine similarity of the angle between them. Again, lower similarity is better because they are samples, they are representations from different classes. And the last 2 arrows, they are samples from opposing classes, but they are both from the minority groups. We measure the cosine similarity. Again, lower cosine similarity means better quality. And then let's see what phenomenon we get in this group imbalance case. So first of all, we will find that if we plot the cosine similarity for both classifier and representation, again, codon similarity, they are always the lower the better in our case. We will see that the classifier similarity is pretty low, so pretty good. But for the representation similarity, they are relatively high. So meaning that the model, when we train the model to neural clubs, we get a model with a pretty good classifier, but not like really good representation. Again, the model is lazy because the model tries to learn something easier. So the learning of a linear classifier is not too hard, even though it's not guaranteed to be the Bayesian optimal, but learning a good enough classifier seems to be an easy task. So the model excel in that task. But trying to learn a good representation may not be as easy, then the similarity is not as good as we see. So that's the first observation. And the second observation, similar to neural clubs like study. So as epochs, like across the iterations, training iterations, we will see that the variance of data inside each subgroup like decrease over time. So meaning that all of the data in each group in the representation, they will shrink to the same direction. Like so that is similar to what has been found in neural clubs literature. So that's the takeaways. We found the behavior of the model. So previously we have theoretical studies. So suppose we have Bayesian optimal and we have like a latent embedding representation. But in this case, we look at what the two components look like in practice. And based on our observation, because learning a good classifier is really easy, but learning a good representation is something the model is reluctant to do. So in order to address this bias issue, what we do is to force the model to focus more effort on learning a good representation. So our approach is like this. Classifier is easy to learn, so we don't like put any effort in learning that. We just freeze the learning of classifier to be a good enough one. And then we will focus everything in our model, like the learning part, to learn a good enough representation. And then the good enough representation means we have alignment of representations between majority and minority groups within the same class. Okay. So that's, again, the geometric perspective. And then the last thing is, because data perspective and model perspective, they're not in conflict. Balancing data is always helpful. So we had to have a balancing like term to have a weighted version of the loss function, and then we can balance data. It's more like to upweight the samples across different groups to have the balanced bias ratio. Sure.
Classifier should be like ETL with so here bronze classifier. Why don't you just use the ETL and console?
Yes, good point. So the reason is using an ETF is fine. So long as you have a good enough classifier, that is fine. Then for here in our practice, in our implementation, we just make the classifier to be aligned with the representation in each majority group. In practice, in theory, they are not the same, but in practice, they are actually similar. So you will find that the frozen classifier looks almost like an ETF. And then here are some experimental results. All of the results just show our work have satisfying performance in different data sets. And also some qualitative results to show like when our model is doing classification, it pays more attention to the, for example, for invariant features rather than spurious features like the background. Yep, so last part of our discussion will be foundation model debiasing. So previously our discussion is based on like traditional models, and the reason we do traditional models is because that may give us more foundational study of like the model behavior. But you will notice that the observation and insight, theoretical insights in the previous study, they also extend to foundation models. I will show you later. But before showing the methodology for foundation model, we want to first clarify the unique challenges in foundation models. So first of all, different from existing study that is usually focused on one specific downstream task. Foundation model have this amazing zero-shot capability handle different downstream tasks. And also, foundation model can usually handle multiple modalities like audio, video, text, image, so on and so forth. Okay. And also another unique or bottleneck of foundation model is the model is really large scale and also trained with large scale data. So in order to address all these challenges, so because the large scale, it also brings some concerns or challenges in terms of computation efficiency. So in order to maintain the zero-shot capability, so meaning that the model after debiasing can still have good zero-shot capability, and also we can do debiasing regardless of the downstream task. And also we can handle multi-modality in the data, and also we want something to be efficient, computational efficient for this large-scale model and data. We propose to have a way to make the unified framework that can do debiasing in foundation models. And unified way can make sure that the model can handle different downstream tasks and can still maintain good zero-shot capability. Multimodality is we handle like VLM, variant language models, so handle different model data. And we have a computational efficient model that can make the process to be fast. And you will notice that the increase in the training time is very minimum, and we only require like 1 GPU to conduct the experiments. Then let's recall, so given all these constraints and requirements, let's see what we do. So the method itself is actually pretty simple. We do that on purpose because first of all, in the previous study, we already found that like addressing the feature separability thing is important. It can handle the bias in no matter what model it is. And then for foundation models, even though we have different structures, they also learn some latent representations. For example, for CLIP model, we have text encoder and image encoder to learn text and image embeddings. And also for diffusion model, we may have the bottleneck layer in the middle of this UNet showing the denoising process. And then we can also treat that as a representation. And then in order to do the biasing, so for all this like observation of the architecture where so at some point we are learning a certain representation, our goal is to do more like editing of the latent representation so as to address the bias. And we believe the method can be used no matter the architecture is, and also after the debiasing, it maintains good zero-shot capability. And because we want to make sure the model does not change too much, the information that is already learned don't get affected too much, we make the model to be pretty simple. And then let me show you some quick results. So we show that stable diffusion model and also image captioning like tasks. And then so the top row shows the existing result, and then the bottom row shows our result after like debiasing. And also we can do text to image generation, like different generative tasks. And later we have other tasks like retrieval, zero-shot classification. All of that is following same concept, like same framework. So the idea here is actually no different than what has been done. So because we know that feature separability is important, in other words, we want to mute the feature separability for sensitive relevant features, but keep the feature separability of invariant or core features. Then in this case, the method we do is we do a random forest, and then random forest give us interpretation of the feature importance. So it shows like across all the latent features, which are related to the task. We don't need to know which are related to task, but so long as we know which are related to the sensitive information, that's fine. And then we can like modify the sensitive feature like data to, if we want to have something say gender neutral, then we just use the same reference value to change as a replacement. But if we want to have a gender specific, so suppose we have a gender specific generation, say give me a like a photo of a man who works as a nurse, then we want to change, like modify the latent representation of the most important features to be the like the feature to be the values of samples who are like most likely to be like male. And then this is the basic idea. We do editing in the latent representation, and afterwards of the training of random forest and editing, we can apply this debias encoder to the downstream task, no matter you're gonna use the encoder for what task. So quick summary of what has been proposed. Unified framework cost efficient because all we need a random forest. And it doesn't need annotated data for downstream tasks because we are using generic data set. No matter what you are using that for, we use Fairface data set to debias an image encoder and bias in bio data for debiasing a text encoder. And also it maintains the zero-shot capability because we are changing the minimum amount of information in the learned model. Some experimental results in text-to-image generation, more text-to-image generation. Because of the time limit, we probably won't go into all the details, but we test on zero-shot classification. This is text-to-image retrieval task and also image caption task. So all of that, we test the performance of our model. Our model is called SFID in terms of the generation quality and also like the fairness or debias performance after this process. So one last slide is showing the efficiency. So because the model is itself, it brings very minimum additional component, just a random forest. The training time takes a few seconds, debiasing a certain image encoder or text encoder, tens of seconds, like around 1 minute. And then the increase in the inference time is also relatively minimum compared with the original inference time. So that's also to show the method is efficient. And then to quick sum up what has been discussed for today, that's slide. So the first thing is, this is a more like a takeaway. So first of all, as we discussed, improving fairness with let me see, I don't think that's the right page. Yeah, we should skip one page. So this is a real last one page. So a quick summary of what has been discussed today. We discussed data and model bias to address data and model perspective to address bias in a model in traditional setting and also in foundation models. And our concept is for the two different scenarios, even though foundation model have something unique, like unique challenges, but we believe the theoretical foundations have some similarity and also connection between them. They share some insights. For example, feature separability and the impact of data bias ratio, they can be shared across different scenarios. And the second is for foundation model, because retraining the model is difficult, then the usual way to debias is to interpret, like find the dimension, direction, or subspace that is relevant to a certain concept, in this case, fairness or bias. And then we can regularize on that, or we can add it along that direction, will be one key way to address the bias. So a few other future directions didn't get covered, but if you're interested, I'll be happy to talk with you afterwards. So one thing is for the introduced method today, so all of that requires sort of data annotation in terms of data label, is this for classification, or in terms of sensitive feature or spurious feature. But in the arrow foundation model, then we may have some implicit bias other than maybe demographic information. We may have something, some bias that is difficult to define. So, and also getting data annotation is difficult. So we want to have a method that can improve fairness with less or even no data annotation. We have some works along this strategy, so happy to discuss if you're interested. And also another interesting direction in the future will be computational efficiency in terms of time, in terms of memory requirement, things like that. And also the last thing we're interested in will be the rigorous evaluation of fairness. So for evaluation, we see it should be like equally, if not more important than proposing a method to do debias. Because if we define the wrong target, if we define the wrong evaluation, then we are kind of focusing on the wrong direction. But rigorous evaluation of fairness is not a trivial problem. Happy to discuss if you're interested, but that will be all for today. Acknowledging my students, because all the works discussed today, they are done by my students. I'm just a message deliverer. And then references for everything mentioned today, and that's pretty much for today. Thank you for your attention.
there is any question in the chat. The chat. Okay, yeah, feel free to ask the question for the remote attendee if you have any.
There is so you make it like deal with technical.
Yeah, good question. So the question is for like the method for foundation models, are we dealing with text or image encoder? Short answer is both. And we use the same methods to address both encoders. Yeah, good question. So in this case, we didn't distinguish because they apply to both. Yeah, but in another work we had is more like zero-shot classification. In this case, debiasing image encoder is more important than text encoder. Text encoder is more like providing the, yeah, exactly, condition, and the debiasing across image encoder is more effective as like based on our observation.
Yeah, I also have a bit for that part. So I think like in the last work you mentioned, you use the random forest in order to find the features that will play an important role for like the gender, right? So I wonder like how accurate this kind of random forest model need to be, especially given the input depending will be pretty high dimension, right? Or is this kind of accuracy performance will actually influence your happiness, because you may only want to find like where is important, but you may don't care about like if it can do a good job in the classification.
Yeah, good question. So the question is, so for here, we use random forest to detect the important features, but what if random forest is wrong? Again, this is not discussed. So we also have similar questions, but they are studied in a different, I didn't get to include, but I can show you the rough slide. So the rough slide shows like this. So we have two axes, and then the horizontal, the two axes shows the quality of, this is zero-shot classification case. So we have two classifiers. One is to show the target, give two text prompts, show the target classification. One is to distinguish the sensitive attributes. And then the two classifiers, the two values shows how good the two classifiers are. And then they definitely impact, so just as random forest, the quality of the classifier definitely impact the performance. But for our method is, yeah, this is our method is relatively stable, but for a like a relevant method is kind of sensitive. So yeah, so that's the rough idea.
Okay, got it. Yeah, thank you so much. Any other questions?
That yes, the question is how to get the frozen classifier. Yeah, so for the frozen classifier, it's more like we can train the model for a few epochs, and then we freeze that. So we freeze the like classifier as the majority ones. So I think it's related to a previous question. So ideally we can set up as an ETF, but how to set an ETF, we need a practice like implementation. So this is more like our practical implementation to get a good enough classifier. Yes, exactly.
And here, and thanks so much again for the speaker to elaborate on photon. And feel free to reach out if you have any further questions on. Hey, great, thank you everybody for attending.
Yeah, thank you for your attention, and thank you for all the attendees from the Zoom side.
Yes. Oh, there seems, okay, just a thank you message.
Yeah.
Okay, awesome. Thank you so much. I will end the recording here.